my name is Kareem Khalifa, and today we'll be talking about the Boolean operators for negation, conjunction, and disjunction. Here's the game plan. I'll start by explaining why this matters, and then we'll go through each one of these Boolean operators and understand the basics of how they work. In order to get a better appreciation of why this matters, let's get a basic understanding of what we're discussing today. Boolean operators are what are called logical or truth-functional connectives. This basically says that you can ascertain the truth of a complex statement on the basis of its simpler components. Here's a useful analogy. Think of a complex statement like a cake. You can then think of the atomic sentences that make up the complex statement as the ingredients. Logical connectives, then, are something like the instructions in your recipe for making the cake out of the simpler ingredients. Because of this, we're in a better position to ascertain the validity and invalidity of arguments. Speaking of valid arguments, here's just a quick reminder. An argument is valid if and only if there is no possible way for all of its premises to be true when its conclusion is false. I repeat, this is the single most important concept in the class. This is the single most important concept in the class. You with me? So pretty clearly, in order to ascertain validity, you're going to need to know the conditions under which statements, sometimes complex statements, are true and false. And this is exactly what you get by having a grasp of Boolean operators. One final reason why Boolean operators matter is that they greatly facilitate our ability to be critical inquirers. Recall that I talked about this on the first day of class. Essentially what we want to be able to do is know when a statement is true or false, and that way we can take the appropriate stance towards it. We can either endorse it or criticize it if we think that's what needs to be done. Okay, let's look at three Boolean connectives, the first of which is negation. In first-order logic, we represent negation with the symbol that you see here. It almost looks like an L that's fallen over on its side. To negate an atomic sentence, simply tack on this symbol to the beginning of it. So for instance, if we wanted to say that Obama is not a Republican, we would put the negation sign, Republican, open parentheses, Obama, close parentheses. Note that in English, we can express this sentence in first-order logic in a multitude of ways. So we could say Obama is not a Republican. We can say it's not the case that Obama is a Republican, it's false that Obama is a Republican, it's absurd to think that Obama is a Republican, etc. Recall our earlier analogy with recipes. In this case, we can think of baking a not pea cake out of pea ingredients. We can represent this, our cookbook if you will, in the table that you see over here, which is called a truth table. Specifically, whenever P is true, not P will be false, and whenever P is false, not P will be true. In this case, it's false that Obama is a Republican, so it's true that he's not a Republican. That corresponds to the bottom row. By contrast, it's true that Trump is a Republican, so it's false that Trump is not a Republican. That corresponds to the first row on the truth table. Okay, now let's look at conjunction, which we represent as an upside-down V, or what's sometimes called a hat. For example, if we wanted to say that Questlove is a drummer and Obama is a president, we would represent that as follows. Drummer, open parentheses, Questlove, close parentheses, hat, president, open parentheses, Obama, close parentheses. Note that all we've done here to get a conjunction is we basically put that hat in between two atomic sentences. Questlove is a drummer on the one hand, and Obama is a president on the other. It's worth noting that there's a lot of English expressions which are represented with the hat, but they don't quite map neatly onto English. For instance, if we wanted to say Questlove is a drummer, but Obama is a president, we would represent it just this way. Now obviously there's an extra connotation with but that isn't captured simply by and, but logically speaking, they function in exactly the same way. In both cases, you're basically affirming that Questlove is a drummer and also affirming that Obama is a president. Unlike negation, conjunction requires at least two statements, right? So you need P and Q. As such, the truth table is going to be a little bit more complicated, and you can see that already. Now let's take a look at what we're doing in those leftmost two columns. What you can basically see is we're looking at all the different ways that P can be true and Q can be true and P can be false and Q can be false. So let's just go through these quickly, right? Both statements might be true. P might be true and Q might be false. P might be false and Q might be true, or they both might be false. And you see that those correspond to our 4 rows. Now when P is true and Q is true, then the whole conjunction, P and Q, is true. This is exactly what we see in this example. Questlove is a drummer, that part's true. Obama is a president, that part's true. So the conjunction, Questlove is a drummer and Obama is a president, is true as a complex statement. Now let's look at the second row, where P is true and Q is false. We've changed our example. Suppose that we claim both Questlove and Obama are drummers. Well, it's true that Questlove is a drummer, so P will be true, but it's false that Obama is a drummer, so Q will be false. So note that it's false that both Questlove and Obama are drummers. Next, let's consider the third row. In this case, P is false and Q is true. For example, let's suppose that the statement is both Questlove and Obama are presidents. Clearly, it's false that Questlove is a president. It's true that Obama is a president, but the whole statement, both Questlove and Obama are presidents, is false. Next, let's consider that fourth and final row, where both statements in the conjunction are false. In this case, as an illustration, let's consider the statement, Questlove is a president and Obama is a drummer. Now clearly, because both statements are false, the whole conjunction is also false. So in general, we see that a conjunction is true just in case both of its conjuncts are true. In other words, P and Q is true if P is true and Q is true, and in every other case, it's false. And that corresponds just to what you see in this truth table. Our final Boolean connective today is OR, that is, disjunction. We represent this with a V. For instance, suppose that we want to say that Maria takes logic or Maria takes calculus. We would represent that as follows. Logic, open parentheses, Maria, close parentheses, V, calculus, open parentheses, Maria, close parentheses. Like conjunctions, disjunctions require at least 2 simpler statements. The simpler statements are called the disjuncts. This means that the leftmost columns on this truth table are exactly like the leftmost columns that we saw with conjunction. And the reason for this is, once again, we need to look at all the different combinations of P being true, Q being true, P being false, Q being false, etc. And that's what we get. We get all the different permutations there on those leftmost columns. One notion of OR you find in English is what's called the inclusive OR. This says when P is true and Q is true, then the whole statement P or Q is also true. For example, imagine that Maria is at a college where you can take either logic or calculus to satisfy the deductive requirement. If Maria goes to a pretty normal college, she can take both logic and calculus and satisfy the deductive requirement too. She hasn't violated the college handbook or what have you. That would be an example of an inclusive OR, which is the way we interpret V in first order logic. Let's contrast that with a different sense of OR now. Let's suppose that Maria takes a break from her studies in logic and calculus and goes to her local restaurant. She orders a meal and the waiter asks, "Would you like soup or salad?" This is a case where she can't say both, at least not without paying extra money. This is what's called an exclusive OR. What it says is P or Q is false when both P and Q are true. This is not the notion of OR at play in first order logic. When we talk about V, we are talking about an inclusive OR, not an exclusive OR. Now let's look at the second row, in which P is true and Q is false. For instance, imagine that Maria very wisely says, "I'm going to take logic this semester," but maybe not so wisely says, "I'm not going to take calculus this semester." In that case, it's still true that Maria either takes logic or calculus. As such, the whole disjunction is true. Next, let's look at the third row, in which P is false and Q is true. In this case, Maria very unwisely chooses not to take logic, for shame Maria, but she does decide to take calculus, which is pretty cool. Note in that case, it's true that Maria takes either logic or calculus, so the whole disjunction is once again true. Finally, let's consider the last row. Here, both P and Q are false. For instance, Maria doesn't take logic and she doesn't take calculus, disappointing both her philosophy professor and her math professor. Note that this is the only situation in which this whole statement, P or Q, is false. In fact, what we say in this case is Maria neither takes logic nor takes calculus.